Hi, my name is Ramana Morgan. My matrix number is 082455.
Hi, my name is Badrul Zahin bin Badur alias Badrul Hisham and my metric number is 083613.
My name is Shaktivel Sivanesawaran and my matrix number is 082962.
My name is Sri Hari Naidu, son of Vasu. My matrix number is 082812.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Farshan Adib bin Muhammad Jafar and my number matrix is 082363.
My name is Walid Kamal Hanafi bin Wahas Nizam. My matric number is 081554.
My name is Muhammad Fakhruddin bin Muhammad Sabri and matric 083713.
Hi, my name is Roshan Sironisan and my matric number is 082709.
A parallel algorithm, in this case a parallel merge sort, achieves parallelism by mainly revolving around the divide and conquer method. This method is repeated multiple times until the subarrays are smaller enough to move on to the next step, which is the merge sort step. Smaller arrays are sorted using a single processor or a thread, and larger arrays are assigned to multiple processors or threads. It can also be said that similar method is used to decompose and distribute tasks among processors. Pipelining is a common method of task parallelism when a single set of data is passed through a series of independent tasks, each executed on different processors. Work and span analysis examines both the total amount of computational work and the longest sequence of dependent operations in a parallel algorithm. Work for parallel merge sort is the same as for sequential merge sort O and log n, where n is the number of elements. This work is distributed across all threads or processors. Span, often referred to as the critical path in the measurement of the longest chain of dependencies in computation. For a parallel algorithm to achieve parallelism through merge sort technique, it is defined as work per span, where work or T1 equals to O n log n, and span or T1 equals to O log squared n. Hence, parallelism equals to O n log n. Amdahl's law is a law that is often used in situations relating to parallel merge sorts. It emphasizes on the maximum theoretical speedup achievable when only a part of the task can be parallelized. Speedup, as shown in the formula, is the ratio of time taken to run a task sequentially to the time taken using multiple processors. In a task that takes t amounts of time to complete and produce results on a single processor, let Ts be the time spent on the serial portion and Tf be the time spent on the parallelizable portion. Hence that T equals to Ts plus Tf. Tasks on the critical path can't be parallelized. This is something called non-parallelizable bottleneck, where tasks on the critical path are sequential, so more processes don't execute the execution time. As a summary, the critical path is the longest sequence of dependent operations that must be executed in order. It represents the theoretical lower bound on execution time, even with unlimited processors. Work T1 is the total number of operations that requires to complete the task. It shows how much actual computational effort is involved. By calculating span and work, we can determine the parallelism of an algorithm using the formula T1 per T infinity. While increasing parallelism can improve performance, it also introduces practical trade-offs due to overhead, such as communication overhead. In shared or distributed memory systems, tasks often need to exchange data. More parallel tasks mean more communication, which can delay the execution time ultimately.